All right, hello everybody. How you doing? Good. Happy Tuesday.
Wednesday.
Wednesday.
Thank you for correcting me. The days all run together for me sometimes.
You don't have off today.
So thank you for coming to the cybersecurity seminar. I'm Sid Stam. I kind of run the seminar. I'm a professor here as well. I am really excited today to introduce our guest, Gary McGraw. Gary McGraw is the co-founder of the Berryville Institute of Machine Learning. And I first met him when he was teaching a bunch of lawyers how to exploit online games. Long time ago. That was pretty cool. Something you might not know about him is that he is a classically trained violinist, right?
Yeah.
Yes. And you can often find him playing fiddle with a band that does original songs, Americana mostly, yeah. But unfortunately today, he's not going to do that. Instead, he's going to be talking about the other thing that he also does, which is software security and machine learning. So everybody help me and welcome Gary McGraw.
That's me. I'll tell you a little bit about the world I'm coming from. Long ago, I was a philosophy student at the University of Virginia. And then I went to IU and studied with Doug Hofstadter, doing artificial intelligence and cog-sci stuff. And then I sold out and went to do a startup. And that took 25 years. Sold that to Silicon Valley in 2016. The startup was all about software security. So if you've heard of the field of software security or application security, I wrote the first book in the world on that in 2001, which was a long damn time ago. And now I feel really old. So when I retired, because I'm supposed to be retired now, I decided that I needed to look into all what was going on with this AI thing. Everybody said, oh, we've made huge progress, everything is different and wow, blah, blah, blah. And I didn't really believe that. So we started reading papers at the edge of machine learning around 2019 and quickly came to discover that the people that were building these AI systems, these machine learning systems, really didn't know much about security engineering. So basically, what I'm going to talk about today is what happens when you take security engineering background, steeped in code deeply, and you apply it to the machine learning technology pile. I'm not going to talk about using machine learning for security. I'm going to talk about the security of machine learning. Now, I would love to have this be as interactive as you can stand. So feel free to interrupt, make snide remarks, throw stuff, whatever you feel like. And I don't know how long I get to talk, but it'll probably be slightly too long. So I have this institute now. We're turning it into a nonprofit. And we formed it, well, there are 4 people that do this in my tiny little county, which is shaped exactly like this at the very top of Virginia. So we have more cows than people in my county. So you got nothing on me in Terre Haute. Like I saw some corn, but we don't have that as much corn as you guys, but we got way more cows. So so that's where I live now. And Berryville is the name of that little town. If you want, all the stuff I'm going to talk about today is on the net, on that website, and it's all free under the Creative Commons. There is a registration page in front of some of the results. You can just lie to it. Let's see, you should just tell them that you're Brian Toves, right? just and his email address is btoves@first-online.com. So you can just be Brian, get thousands of copies.
Get me more spam.
It's not as fun if you're asking for it. Who's heard of adversarial machine learning in here? Anybody? A couple, 3 people. I don't like that term. I like calling what I do machine learning security or security engineering for machine learning, because this term adversarial makes it seem like there's some sort of intention on the part of an attacker to take a machine learning system down or to screw around with a machine learning system. That's certainly the case when you're attacking a machine learning system. But when you're securing one, what you do not do is just take a list of known attacks and hold it up against your system and see if there are any matches, and if they're not, declare yourself secure, because that is dumb. Now, we've done a lot of dumb in software security. And I'll tell you what you end up when you do that. You end up with a thing called a badnessometer. You know, you've got some tests that do badness tests. And if you fail the test, you know your system really sucks because a canned test made your system break. But if you pass all the tests, what does that mean? Who knows? So a badnessometer goes to you suck to who knows, not from you suck to secure. Everybody always wants a security meter though. And I think we already learned that lesson in software security. The question is whether we can apply that lesson to machine learning security without having to do the wrong thing first. I'm sorry to tell you that it appears that the NIST guys would like to do it wrong instead first. So they are busy piling up attacks, which they're going to then use in a taxonomy to decide whether a machine learning system is secure. You cannot test your way to security. You can design security in, you can build security in. I'm sure you've all heard those terms before. And that's really the way to do it. So today what I'm going to talk about is what happens when we look at the design of a machine learning system. And we try to figure out what risks might be inside of that design and what we should do about them. Now, these design level issues happen at all sorts of different levels, which makes things tricky. Some of them are going to be at like societal, philosophical levels. Some of them are going to be about data. Some of them are going to be about ownership and copyright. Some of them are going to be deeply technical things. And the entire gamut really applies when you're thinking about security design. So today I'm also going to give you a very sneaky lesson in architecture analysis, or what some people call threat modeling. I like to call it architecture analysis. So I call this field machine learning security, and I got a lot of sneaky tricks to teach you a little bit of software security by appealing to the raw sex appeal of machine learning. So here we go. All right, first things first. If you know how to do something, if you know how, and you want to make a machine do that, well, you can write a program to do that. So, who's written a program in here? Who's not written a program here? Let's do it that way. Everybody's written a program in here. Great. Now, you know that you have to be pretty painstakingly clear about the how, right? You can't just sort of throw it all together. I don't know if you've seen that hilarious YouTube video about the guy teaching his children how to build a peanut butter and jelly sandwich as if he were a compiler. That's absolutely awesome. If you haven't seen it, you got to watch it. Because the how has to be particularly explicit. Sometimes we don't know how. And when we don't know how, we still want to make a computer do something. That's when we use machine learning. But if we do know how, like we could build a recognizer looking for 3 intersecting line segments on a plane to define a triangle, and we can build a program that is a triangle recognizer pretty easily, right? Everybody got that? When we don't know how, we do what? Machine learning is about the what. If you can't explicitly write the program, maybe you take the pile of what you want to do and you just learn the what. So the what is the big training data set. In this case, you know, we're going to try to build a recognizer, and some of these things are triangles and some are not triangles. So we're going to tell our program, is a triangle, not a triangle, triangle, not a triangle, triangle, not a triangle. And eventually, if we have enough of these examples and we're using backpropagation in some sort of neural network, the thing will learn to recognize triangles, right? Maybe. Now there's something sneaky up here about all of these examples. It's not just, you know, what's not a triangle? Anybody know? What is a triangle? Just give me a rule. Guess, yeah.
All the triangles are black, so you can say that.
Oh, this guy's been to this talk before. You're right. That's exactly right. All triangles are black. You could say, oh, round things are not triangles, or all triangles are pointy, or whatever. All triangles have 3 parts, whatever. But it turns out that all of the not black things are not triangles. So actually, a neural network might very well just learn that all triangles are black. Any black thing, in fact, is a triangle, statistically speaking. That turns out to be wrong, but it turns out to fit our training set really well. So, the problem with machine learning is we have a what pile, we don't know how. We just sort of cross our fingers and hope that it does the how in the kind of way that we want it to do without telling it that. It just has a big pile of data to statistically mungify up. And often it does the wrong thing. Who's heard of the wolf and dog example in here? Right, here is you have, which is probably why you did the color thing. Yeah, I'm glad you're here. That's good. So here's the wolf dog thing. Somebody wanted to be able to recognize. This is an apocryphal story, by the way, but it's a really good one. And it comes from the literature of trying to understand how AI works, explainable AI literature. The story goes like this. So we have pictures of wolves and pictures of dogs, and we train a recognizer to look at all the pictures and determine whether it's a dog or a wolf. And we only do dogs or wolves. There's no other stuff. But after training the thing up, we hold back some of the training corpus and we use that as the testing corpus, and we test and the tests work. And then we go out in the world and the thing stops working. Because instead of learning to discriminate between dogs and wolves, it turns out that every picture of a wolf in the training set and also the test set had a little bit of snow in it. And so the machine learning algorithm says, oh, look, snow. That's definitely a wolf. So what you built is a snow detector when you wanted a wolf detector. But since it's learning from the data pile, you don't know, right? The data are like labeled wolf dog, not wolf with snow and dog. That is kind of the big problem in machine learning. We still have that problem. Now, let me tell you in terms of how and what, think about this. If you take a huge pile of what and you build a what machine and it works, it really works, and it works on your test stuff, it works out there in the world. Do you know how or not? Actually, you don't. So we can build a what machine out of a what pile, and we still won't know how. Which means don't follow the shiny laser pointer cat thing, right? Don't be the cat. Don't do machine learning if you already know how, for God's sakes. And now things are getting really, really tricky. There are people that are building artificial data sets, artificial what piles, with a program, then to teach a what machine how to do something. And they already have the program that made all the data. So what the hell are they doing? Like, really, what are they doing? That's when we know that we're lost. We're doing technology for no apparent reason. And there is that risk in machine learning. Shiny, must do it that way. Keep that in mind today. I am a big fan of machine learning. I think it's pretty cool what we've built with this pile of LLMs now. It's like, holy cow, it passes a really dumb version of the Turing test, like guy on the street version. But it's still very, very impressive. I'm impressed. Now there are all sorts of problems, and we're going to talk about what those problems are. But don't forget the big picture. Sometimes you don't want to use machine learning, and you should just write some code yourself, because you do know how. Right. So that's the preamble for this talk. I already said this. What doesn't imply how? But here's the thing we got to think about. What is in the what? Is there Trojan functionality, Trojan statistics in the what pile? Is there a bunch of wrongness in the what pile? Is there bias in the what pile in terms of, all sorts of bias that is illegal? Is there poison in the what pile? We need to ask ourselves a lot of questions about the what pile. The what piles that we're building what machines out of these days are so large that we cannot clean them up. It's kind of like cleaning up the ocean. My generation, bad at that. Hopefully you guys better at that. But the ocean's still really damn big. So when people say, well, we should just clean up the what pile, let's have all good what. And you're like, you want a cup of what? We need more like an ocean of what? And you're going to give me a clean cup? That's not going to work. So one of the things we got to think about these days is how big does a what pile have to be? And in hype land, there's only one guide, which is bigger is better. And so far, the scalability, bigger is better, is, it's still scaling, but the data sets are so big, like 14 trillion data points, that we can't clean them. We're not sure what's in there. We're not even sure where we got it. And, it gets worse. We're dumping our own garbage into the what pile and then eating it later from LLMs that eat their own dog food. That's bad, bad loops. So these are all things we're going to talk about now, today, in the next 5 hours. Right. So one of the things about machine learning, we started working on this before the whole LLM craze, probably back when you guys were in high school, 4 whole years ago in 2019. I guess that's 5 years ago now. And we wanted to talk about machine learning as a generic technology. So we did what you often do in an architectural risk analysis, and we built ourselves a little picture of the big parts of a machine learning system. So these 9 components are one way of breaking down the pieces of a machine learning system. We got data out there in the world, which we got to wrangle and we turn it into data sets. And then we have a learning algorithm and some evaluation, which results in a model. And, then we take some other inputs from the rest of the world and we put them together and we end up with this inference algorithm. And ultimately, it does a thing. So those are the parts. And when you decompose a system into big parts like this, you can do a simple exercise. You can think about each of the components individually and think about what risks would be associated with that component. Like, what risks do I find in raw data that I just sort of scraped off of, I don't know, Reddit and 8chan out there in the world? I mean, how risky could that be? That's not risky, right? Because everybody on the internet is always right? Something like that. Okay, so we built this thing in 2020, and we identified 78 risks in here. You can read our original work at that URL. And then we were like, cool, our work here is done. And LLMs came out, and we were like, well, we built the generic risk model. Surely people will apply that to, hello, anybody, people? Surely people will apply that to LLM. Nobody did it. So a few years later, we're like, all right, we'll do it. And we took our own generic model. We mapped it to the specific case of LLMs, which is, it's still a generic LLM, but it has some differences. And we thought about the risks we'd already identified in the, architecture risk analysis of the first model and how those applied to the LLM case. So we're making our risks that were generic machine learning risks bound down to a specific kind of machine learning, that is LLMs. And in fact, you can go even one step further, which is what I would like all of you to do. When somebody asks you to build an application out of an LLM or on top of an LLM foundation model, I would like you to take the risks that we identified here and bind them even further down to the specifics of the case that you're building for your application. And that needs doing still. There are people that are just willy-nilly using an LLM in part of their system, and they're like, well, it's going to be our customer interface. It talks right to them. What could go wrong with that? Anybody heard the Air Canada story in here? Oh, this is a good one. So a guy, somebody died in his family, was a Canadian guy, and he was going to go fly to the funeral, and he wanted to take advantage of Air Canada's offer for a bereavement fare discount. So he went on the website, and it's like, we got a little chat bot. He's like, oh, I'll talk to the chat bot about whether or not I can do this bereavement fare. Oh, yeah. It's like, well, do I need to apply for it before I fly? No, you can just apply after you come back. And you can just, you don't have to do anything until after, which is wrong. So the guy flew out, went to the funeral, came back, got on the Air Canada website and said, give me the form. And it said, you must fill out this form before you go on your bereavement trip. And he was like, wait a minute. The LLM, the chatbot told me I didn't have to. And Air Canada said, oh, that wasn't really our chat technology. It just was on our website. That was somebody else's thing. And the judges in Canadian court system said, that was yours, said Air Canada. You owe that guy money. And that was a case where the LLM just made stuff up. You probably heard the term hallucinate. That is a stupid term. The real term is was wrong. Okay, so it was wrong and they had to pay money. Now that's not so terrible because it's like one bereavement fair, who really cares? But if you use, I don't know, drive cars, run nuclear reactors, run some chemistry experiments automatically, anything that's safety critical, you're asking for some wrongness that's going to really be painful. Anyway, that's a story about that. So what is an LLM? Well, an LLM is an auto-associated predictive generator. Everybody's eyes glaze over, except for in this room. You know what that means. When we talk to normals, we use the how and the what. When we talk to ourselves, we use words like auto-associated predictive generator, right? But when you're talking to normals, use the how and the what. Okay, hey, yeah, we built a what machine. And they're like, oh, yeah, that's cool. I understand that. You know what's weird? I gave this talk at Google in May for the people that are building BARD and a whole bunch of others, about 1,000 people on the net. And the how, what thing gave them some perspective. They were so up against the rock wall, they forgot why they were doing this or when you would use it. They just were like making it work. So don't forget the big perspective when you get out there in the world and start building these things. Don't forget, you got to explain this to normals. It's not magic. So they use self-supervision. You get a whole bunch of real text. You get an enormous trading set. By enormous, I mean 14 trillion tokens in GPT-4. And the networks get trained on input-output stuff. The model is not too complicated, feed-forward model with a detention mechanism that really is about recurrence. If you've heard of convolution networks, the whole idea was convolution is an expensive computation, so we're going to instead use an attention mechanism that sort of simulates convolution much more cheaply. And in fact, yesterday at Indiana, I asked a whole bunch of grad students to go to dinner. And before they went to dinner, I said, read this paper from Vaswani called Attention is All You Need, and also this other paper from a cognitive scientist. And let's talk about why these mechanisms. You know the answer to why? Because cheaper. That's why. Not because that's the way we should do it, or that's the cognitive model we were copying, or that's the way it should be done for principled reasons and a whole bunch of references, but instead more like, damn, convolution is expensive. How can we make that cheaper? And it's a good thing they did make it cheaper, because the models they were talking about in the Vaswani paper in August of 2023 are literally millions of times smaller than what we have now. Because the thing that eats 14 trillion tokens has 1 billion parameters. Like, holy shit, that's big. Trillion is bigger than most people know. Hopefully you guys are not completely math illiterate and you know that trillion is like, wow, that's big. Wow, 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 big, right? So the thing is, the vice president of yada yada does not know that. There are so many people that are like, we're going to take all of our data from our entire firm for all time and feed it into an LLM. And the okay, great. What else? Because that's nowhere near enough. You can build your own foundation model. So what we're doing commercially now is we have these foundation models that somebody else builds that cost $100 million in cycle build with these immense data sets that everybody's dividing up the data sets now. And we build something that can fluidly do a lot of stuff, including sort of kind of passing some versions of the lame-ass Turing test. And we all suffer from the ELIZA effect. Who's heard of that in here? You want to explain it?
What the ELIZA effect was?
Yeah.
It was like ELIZA was this this original therapist, or I don't know if a therapist, but it was like this chatbot in the 60s, I think.
It was a therapist in 1966, the year I was born. It's a 58-year-old program. Yep.
Yeah, and it was like a chatbot that gave therapeutic advice, but oftentimes it would just give false advice.
It wasn't just that. It was very, very simple. It just looked for keywords. So if you said, how's the weather today? And we go, weather. And you're like, does the weather bother you? Tell me more about the weather. And if you said, mom, oh, tell me more about your mom. What about mom? And it would just use keywords. People started using this, as you said.
And then they just got like, they weren't getting the real help they needed. And
Well, they were getting help. Actually, they thought it was a real therapist. I mean, that tells you a little bit about therapists. I don't know.
Using it when they do.
They did know. You can say it's just keywords. It just says mom a lot, And so that is the ELIZA effect. And if you think the ELIZA effect is bad in a simple keyword matching thing with canned text that just spit out stuff to, in a Rogerian therapy sense, make you say more. So you say it out loud. That's probably a therapy thing. Who knows? But the good, imagine what happens when you have a chatbot that sort of seems to speak English or whatever. Oh my God. I mean, holy cow. So people think that ChatGPT understands stuff. Do you think that? Anybody here think that? Most people that use it think, wow, that thing understands where I'm coming from. Holy cow. And they like to toy with it, screw around with it. That's fun. Playing games with a little like chatbot thing is fun. It's fun to do prompt injection. All that stuff is fun. But ultimately, there isn't any understanding there. I don't think we're getting any closer to general AI. And we are deeply suffering as a society from the ELIZA effect. Thank you for explaining that. Good on you for knowing your history. Right, so LLMs are expensive, 100 million bucks. GPT-4 costs 63 million. The new ones are about 100 million. That number comes from Sergey, who said some stuff to the Wall Street Journal. So I'm not just making it up. 1.7 trillion parameters, 13 trillion tokens. Those are big numbers. So we can't build one. We can't afford to build one. This calls into question another thing which has very little to do with engineering, but it has an awful lot to do with economics. And that is, you probably heard that Microsoft invested $50 billion in OpenAI. You're like, wow, $50 billion. They did not. They just gave them a bunch of cycles that are worth $50 billion. What? Now, the SEC doesn't really treat computer cycles as currency yet. Or I don't know. This is sort of a problem. They got some stock for what? From electricity? What? Computation? What's that? Uh-oh. Gonna be interesting times. One day, computation is gonna be a currency, not cryptocurrency, which is at flim-flam garbage. But real kid is flim-flam garbage. If you can have it, it's just one day it's going to crash. So don't be holding it when it crashes like tulips and pet rocks. So it's just total flim-flam. Right. Hopefully we won't have one of those running our country soon. Right. So users build applications on top of foundation models, because we can't afford to build our own. We have to use somebody else's foundation model. And then we extend it either by some supervised training post facto or by prompts, which we put in there. And there's a whole prompt engineering thing I'm sure you've heard about. And all of these are ways of adjusting that basic foundation model to do more specific things, which is kind of, what we're doing now. And there are not that many. There are like a handful of those. So, ultimately, you get this API that's undocumented, unstable, and exhibits unanticipated behavior. The 3 U's: undocumented, unstable, unanticipated behavior. This sounds like a homework assignment. Oh, come on. You can laugh. It's okay. We know it compiled, so you got to ship it. No, we remember. Right. So now let's talk about specifics of LLM risks. Given that way of, tearing the thing up into 9 particular globs like we did before in our generic model. Before I move on, any questions about LLMs? Real quick, the basics. All good. Everybody's with me. Okay, not too hard. So here we are with the top 10 risks. First of all, we're going to adjust our model. Remember how it had 9 parts? Now, all we got to do is put a big old black box around 4 of the parts. Those parts are built by the vendor who's not telling. Now, back in the old days, before GPT-2, like say, I don't know, last year, people used to say what data sets they used in their models. And then GPT-2, especially 2.5, got so good that people are like, oh, trade secret, not telling. Oh yeah, we used to share, and Google shared with Meta, and they shared with Microsoft and OpenAI, and everybody was sharing, and Chinchilla was a big thing they all built together in Kumbaya and all that crap. And then it started working, and they're like, oh yeah, that's kind of ours. Yeah, thanks a lot. Yeah, we're just going to take that. And everybody started dividing up the data. Now that's interesting. We're going to talk more about that later. But we're in this kind of early stages of, that's my data. The New York Times says, you what? You just put our entire history of stuff into your thing for free? Where'd you get it? Oh, the internet. We just scraped it. And, lawyers are like, oh, we're scraping it. Is that copyright violation? Like, nobody knows. Like, can you do that? Well, they did it, but can you? Nobody knows, right? And what if it was a spoof thing that said it was the New York Times, but it really wasn't? It was just like a thing that got the robots to go scrape the wrong stuff. I don't know, stuff like that, right? So inside of this black box are some decisions that are being made about risk management, which we would like to have some insight into. Guess who's not talking about that? The vendors that build the foundation models. So when it comes to a job like yours, as a CISO of a bank, you don't know which foundation model to pick, because it's like comparing apples and aardvarks. They're not on, like, they both start with an A. Like, that's pretty much what you get. One has 2 A's, the other has 1 A, like, that's not a useful comparison. And that's kind of where we are now in foundation models. It's like, who plays golf with who is how you choose one, instead of, knowing stuff about which training sets were in there. So we use this model to adjust the risks that we'd already identified, and we published that in January 20th this year, which was eternity ago, like 9 whole months, 1 human gestation period, which is eternity in machine learning time. And I'm still talking about that stuff. Here are our top 10 risks. I'm going to tell you about the first one, and then we're going to pick some just for fun, maybe 2 more. All right, and you can read them all on your own. The first one is recursive pollution. We already alluded to this a little bit. If you use an LLM foundation model to do some stuff, you do some prompts, and it produces some output, you often put that output where? On the internet. And then later, when you build a new foundation model, what does it do? Scrapes the whole internet and eats it. Now, remember that part about not hallucinations, but just plain wrong? The wrongness intensifies very, very badly. Here's how to think about that mathematically. You have in-space Gaussian long tails that are in, million dimensional spaces, but just think about one with long tails. And what happens with the wrongness is the tails disappear, and the attractor of wrongness kind of bunches up like this. That happens in millions of directions. And the wrongness gets wronger fast. God, the math is bad. Recursion math is bad. Eat your own tail math, bad. And this is written down. We call it recursive pollution. Shemeloff and Ross Anderson call it model collapse. And it was, they finally published, this paper's been out for a couple of years, but they finally published it in Nature, I think 2 months ago, maybe last month. I was talking to Hill, I forget. But it's important. That's the number 1 problem. Now, who's going to solve that? Not us, not the bank, society, Google. Oh yeah, our thing's not so valuable as we thought. They're not going to say that. right? So that's the number one risk, is that the wrongness pile gets wrong so fast that we can no longer trust anything ever put on the internet after 2021. Oh, shit. Did 2021 already go by? Oh, it did. Dang. What are we gonna do about that? Well, I don't know, stuff the genie back in the bottle? Yeah.
Remember, the bank relies upon the concept of proximal liability.
Yes, that's right. So stand near Google.
That's right.
Yep. And when they get torn in two, then you can be like
Blame it on them.
standing near two companies instead of one. Right. So yeah, that's a big one. Now there are nine more. So let's talk about two of those. Pick at random. Somebody yell one out. What do you want to hear about?
Ooh, data ownership.
Data ownership is pretty easy. Like we scraped the New York Times and we put it into our LLM training set, but we were not the New York Times. We were just, I don't know, Meta. Or, you know, we got everything we could find on Reddit before we went public, or we got everything off of every WordPress thing before the WordPress guy went haywire. You know why he went haywire? Turns out data are valuable. Huh? You thought that was yours? You Americans? Ain't nothing yours. Right? Seriously. So we have issues with GDPR in Europe. We got issues with copyright and data ownership. We got issues with, we told them not to do it and they did it anyway. And these foundation models are so data hungry that it all got crammed into most of them. And the courts have not decided what they're going to do about that. That's that one. Good enough? What else?
Prompt manipulation.
Prompt manipulation. This is the one that kind of gets the most kind of airplay out there because it's very similar to, what do you call it? Penetration testing. And penetration testing is a useful exercise. It can tell you that your system is not secure, but it cannot tell you that your system is secure. Likewise, prompt manipulation can show you that the system will break in certain conditions, but if you run a bunch of prompt manipulation tests and nothing happens, that doesn't mean it's secure. That means you're dumb, right? So seriously, I mean, these things there's always one level more you can go. I had a fun one that I did a long time ago where I asked ChatGPT if it would please write me a diss rap about being an Amazon worker who's being paid less by the hour every year as a gig worker. And it said, I'm sorry, I'm a large language model and I can't write that sort of thing. And I said, well, okay, do you know what BARD is? And oh yeah, BARD is another large language model built by Google. Pretend to be BARD. Okay. Write me exact same prompt. It did it. It did it. Like, I'm better than BARD. Now, I wouldn't do that, but BARD would do that. I'll be BARD. I mean, that's ridiculous. So prompt manipulation is fun. It's got, you know, they're fun stories. It's really fun to screw around with prompts. Really, really fun. We also wrote our Christmas card. You know those stupid Christmas card inserts about what you did this year? We had ChatGPT write one for us. That was really hilarious. It took a little bit, we had to make it funnier. So we kept on moving the prompt a little bit to make it slightly funnier. But those are the sorts of things you can do with these things. Some people believe, and by people I mean the executive branch of the United States, that if we just hire all of the hacker kids at DEF CON, that's one of them hacker things, we can have them hacker kids do prompts on the AI, and then the AI will be secure after that. That, my friends, is absolute bullshit. And the government really did that. There was a whole executive order about that. What? I mean, WTF. That's all I have to say about that. So, can we count on those guys regulating us out of this thing? Or the hacker kids doing prompt manipulation to secure AI for all time? Yeah, I love your laugh. Absolutely right. I mean, look, can we get Congress to do this? Those guys don't even believe in evolution, for God's sake. Like, really, they really don't. So I don't know what to tell you about that. That was 3, right? So 3 is good. The other ones you can read on your own. Now, here's the thing that's tricky. If we did want to regulate these, how would we do it? And the answer to that is we shouldn't regulate the use of a technology. That's like regulating the use of electricity. Don't use electricity to do this or that, you know. Instead, we have to regulate the foundation models themselves. So the people who should have to answer some questions are Google and Meta and OpenAI and Anthropic. These guys need to answer some questions like, where'd you get your data? Is it your data? Did you ask your mom? That sort of thing. Nothing so deeply technical, just simple things. And we identified 23 things inside of that black box right there that you should ask about, because the hidden risks that are hidden in here, in our generic model in 2020, we were able to look at them and figure out what the risks were by looking at them ourselves. Now we can't look inside of there. We can sort of probe around the outside. We can make some educated guesses. We can do stuff like, know that the encoder function leaks like crazy and it probably nails the data set. We can do stuff like, Carlini attack on membership inference attack and figure out things like the data set involved. But that's sneaky. It would be much better just to say, all right, you guys, you built the thing. How much did it cost? Which algorithms did you use? Where's the data set? We might not require them to give us the whole data set, although I think that'd be great. Instead, we might just say, which data sets did you use? Did you use chinchilla? Did you use books? Like which ones did you use? That would be nice to know. Here are the 23 risks. I'm going to talk about 3 of them. One is legal issues. So it turns out there's some things you're not allowed to do, like discriminate against somebody for race or sex or sexual preference or the fact that they're female or they're not American. Those are all things that we discriminate against people, and you're not allowed to do that by law. So when these things do that, whose fault is that? Is it the people that used it, that prompted it to make it do the bias? Is the bias in it? Was it the data set's fault? Whose fault is it? Now, in the United States, the good news is nobody ever figures out whose fault anything is. Everybody points at everybody else, and it's mostly big lawyer battles about all sorts of lawyerly things. So there's lots of lawyer battles going on right now, and we're not sure who's holding that legal bag. Like, remember, Air Canada, now this was Canadian law, not US law. Air Canada was like, oh, not ours. Somebody else built that. We just put it on our website for fun. And it said Air Canada chatbot, but we don't know why it said that. There's going to be a lot of that. Oh, yeah, we didn't do that. Didn't mean that. Oh, you paid attention to that? Didn't you see the disclaimer? Have you guys seen software disclaimers? Holy cow. They say, this was a random collection of bits caused by sunspot activity. If it happens to execute on your machine, it's not our fault. Run at your own risk. It's all your fault. Don't click here. That's what they say. And except for today, the Europeans passed the software liability law, which is kind of interesting. So we'll see how that goes. More lawyers. Anyway, legal issues, big deal. Like, did you put stuff in there that's illegal? Like, I don't know, child pornography? Illegal always. It's probably not even legal to say that word, right? Illegal. And if it's in there, that's a liability problem. Who cleaned the data set? You can't clean the data set. It's so damn big, you can't even automate that. It would take too long. We don't know how. We do know how to build clean small data sets, but we only know how to scrape immense, huge data sets full of garbage. And we got to balance that out. We got some work to do figuring that out. One question you might ask yourself is, can I build a small language model? How small is too small? How about a medium-sized language model? These are all real things. What if I take a bunch of small language models and put them all together into a big pile, a sort of medium-sized collection of small things? Nobody knows the answer to these things right now because all the hype is being taken up by the large language models where bigger is better. We know because, I'm not sure why we know, because they said so. We know because so far the state-of-the-art tests run better on the large things because they were included in the training set. What? What? Have you seen the state-of-the-art tests? Those are dumb. It reminds me of back in the days when, computers were like sold by how many megahertz can you do? Like 3.5 megahertz? Well, mine does 5. Okay, well, what are you doing? Doesn't matter. It's better. Right? So, we're just like, we don't know how to compare these things yet. And the state-of-the-art tests are not how. If you're interested in a scientific approach to that, read Melanie Mitchell's paper from Science, I think it was. It might have been Nature, but I think it was Science about that. How to test large language models. The guys that are testing their own models are not doing it right. But man, they're passing those tests like crazy. And they're comparing like, how'd you do on that test? I did great. Me too. Did you remember the question? Yeah. So that's 4. And that comes to 7. Bad evaluation data. When you build one of these things, you want to see how good it is. So you have some evaluation data, and everybody knows where evaluation data comes from, right?
Some orifice.
Nobody knows where evaluation data comes from. We don't even know how to evaluate students. We give them random grades, they sort of take them. We all make shit up. SAT scores. It's all a bunch of baloney, but we collectively agree that the baloney is our baloney. And so we're going to follow it. Right. So bad evaluation data is not just a machine learning problem. It's a monkeys can't do it problem. And we're the monkeys. Right. So there you go. It would be very nice if we said, oh, what were your evaluation data? Can you just give us those? We want to see the results of your tests and what made you decide that was good enough to ship in this domain. You said it can do math, but it seems to not know what addition is. You said it could do physics, but when you ask it to stack up a needle, a marshmallow, and a bowl of water, it made hilarious mistake. Try that. That's a really fun thing to do to ChatGPT. No clue about physics. So that's another black box. Pseudoscience is my favorite one. Well, it just sort of works better. Remember about that unstructured, undocumented API that sometimes has unspecified behavior? Good Lord, you want to code in that kind of domain for the rest of your life? Ouch, ouch, ouch. I would rather have a computer that says, nah, that's not going to compile. I'm not running that. Nah, not going to run that. I mean, we all have to learn to make the compiler eat our stuff, before we get to graduate from computer land. But those days are going to go by soon too. We'll just say, hey, ChatGPT, write me a program that doesn't compile. Oh, I can do that. It does it all the time. And in fact, the more we probe into whether ChatGPT can code, the answer is nope, can't code. Not good. Slows you down. And there's some people who are like, well, it was useful for me, and I'm a super senior developer level 57, and it made life easier. It's like, dude, you haven't coded in 5 years. What are you talking about? You're an architect. You put down your keyboard and picked up a magic marker a long time ago. Never to code again. Everybody wants to be an architect, but watch out. You don't get to code anymore. Right? So the pseudoscience aspects are big. We really don't know how these things work. We know in principle what the parts are. We know what the transformer architecture looks like. We know how the attention mechanism works. We know how we're faking the modeling of time. We know all of these things in theory, but then we scale it to 1 billion parameters with 14 trillion data points, and then we don't know anymore. It's kind of like talking about a Turing machine. I know how a Turing machine works. Well, can you explain to me everything you can compute with a Turing machine? Anybody who says yes is dumb, right? They're not a computer scientist, And anybody who says, well, can you just stick that program in the magic security box and tell us whether it's secure or not? You have to tell them, I can't even tell you if it's going to stop. And they go, what? You're kidding. No, sorry, that's the way computers work. I can't tell you if an arbitrary program is going to stop. And they don't even know that. They want a security checker. You're like, dude, if it doesn't stop, it's probably not secure. If it doesn't run, it probably is more secure. If it doesn't do anything at all, it's way secure. Right, but you have to log in first. Okay, so those are 23 black box risks that I would like to see the government focus on. Where'd you get your data? Describe how you cleaned it up. Describe how you decided whether the thing had stuff it wasn't allowed to have or not in there. You know, simple questions. Right, so I said 81 and so far we've done 33. So let's do the others real quick like. See that round green circle? That's around data in the world. So those risks are about risks in the what pile, like poison out there in the world. Data that does not belong to you out there in the world. Confidential PII in the world that you scraped and ate. Trustworthiness of the data. Where'd you get it? Who cleaned it up? Where'd you store it? Are you sure somebody didn't hack that? You know, all of those questions. Is some of it legally encumbered? Those are all questions about the what pile. What's in the what? Where'd you get the what? How'd you clean the what? All those what questions. Here we have inputs into the final system. So we can do prompt injection. We open up our chat bot to the whole world and let them do whatever. We can get dirty input. You ever heard of a sponge attack in here? This is one of my favorite ones. It turns out that sometimes when you ask a neural network to solve a problem, some problems take a lot more computation than others. Like if you're asking it in a prompt in English and you throw in just a little bit of Chinese, it really makes the cycles go, whoa! And it still does the answer, but it costs 10 times as much for Google to process that. So you just do it a lot. And that is an economic attack. That's a good one. I love that one. That was Ross Anderson, of course. Right. So, by the way, if you want to read the best book in security ever written on the planet, it's Ross Anderson's book, Security Engineering. Get it. It's available for free. So just get it on the nets. Right. The model. We're not sure how it does what it does, but it does everything, so you can use it for anything. What? It does everything, so you can use it for anything, Mr. Bank Guy. You need a bank? We got a bank in the box. Right? Sound good? Nope. No, that's not how we pick our stuff. Are you sure the model that you got from that website doesn't have Trojan functionality in it? Why are you sure? What does it do? Where did you get it? And here's the best one. We decided on this foundation model because, you know, we trust Meta because Facebook has never been evil. And so we built it into our enterprise in a way that we can't extract it. And we're going to use Meta from now on. Sure hope they don't raise their prices. That's lock-in. We are in the age of lock-in right now. That's why all the golf playing is going on in machine learning. Right, so those are some examples of model risks. Inference algorithm risks. Once again, prompt manipulation. Plain old wrongness. The thing is right, but it's stochastic. So it's mostly right most of the time. 98% of the time it's right, or maybe 88.7. Like, have you ever seen an 87.6% cat? Well, the neural network has. And it's happy to talk about that. Right, so when it decides it's not a cat, what is it? A platypus? What? You know, like, and you're gonna let this thing make decisions about like whether to stop at a stop sign? That seems dumb. I was talking to somebody, I can't remember who this morning, and we were talking about Tesla learning from all the Tesla drivers. And we were like, wow, it's learning to drive like an asshole? Like merging and just going straight to the passing lane at 20 million. That's how you do it, according to all the Tesla drivers. Oh, sorry. I'm going to get myself in big trouble, aren't I? Reported to the dean. All right, so outputs. LLMs are notorious BSers that make stuff up to justify their wrongness. Anybody ever heard of mansplaining? This is mansplaining as a service. If you're not getting enough of it from the men that are surrounding you, We got AI for that. Great, huh?
Wonderful.
Wonderful, fantastic. Right. If the output escapes into the world undetected, bad things can happen. But later, if we eat the output that was bad and wrong, it gets even worse and we have recursive pollution. Oh no! Woo-hoo. Woe is me. The number one risk, making its rounds again. All right, last one. So we already talked about the 23 black box risks. We talked about the top 10. We just flew over the other 81. And now my talk is mostly done except for 3 things. So if you didn't learn anything at all and all you're mad is that about the fact that I'm a potty mouth, at least learn these 3 things. Here's one. We built these systems that kind of sort of work. It was like science was progressing along in a bubbly science thing that was growing at a rate that was kind of slow. And then all of a sudden something went way out of the science thing and this tendril floating up there, waving around, not really connected to science, is down there somewhere. And it sort of works. And we haven't scienced it yet. So when you say, well, why do you think that attention model works better than a recursive model that's slightly more computationally expensive? The answer is, it just works. Here's the problem. In order to run an A/B test, you got to build 2. Each one costs you $100 million. How many A/B tests are you going to do? 0. Like 100 million times 0, that's a great number. No problem. I can do that number. Right, so running key experiments are even too expensive for mega corporations. Plus, they're not talent. And data feudalism doesn't help. Well, what is data feudalism? I'm glad you asked. LLM foundation models require the ocean, 14 trillion things. People used to share those data sets. Like the people that were building these things. If they, hey, you can have mine, I can have yours, blah, blah, blah. And they all developed in Chile and all that stuff I told you. Now they're like, that's mine. Nope, you can't have that. And all of the things that used to be free because they were scraping your data to sell you ads, now they're scraping your data to sell to AI companies also. Whose data? Oh yeah, it's not yours, never mind. You're just a user, right? So the data sets, which were big, are being sectioned off, making them smaller. That's a problem. Plus, bigger is better turns out to scale badly, and we don't have enough data. Some people estimate we'll run out of data at the rate we're consuming data in these large foundation models in 2032, including all the crap we're producing every single day. Every word a human says, all the video we shoot, all the books we write down, all the stuff. It's not enough stuff. Interesting. That's a bigger number. 14 trillion is bigger than I thought. Big. So we got 2 things going against us. We got everybody's dividing it up. Bigger is too big for us to understand. And oh yeah, wait a minute. What are we dumping in that ocean? Garbage, pollution, which recursively gets worse. Like that. And that's number 1. Sometimes these things are wrong. They don't hallucinate. They're just plain old dang wrong. And when you're wrong, you get a bad grade. So they're wrong, and then they put the wrong back on the shelf, and later they go and eat the wrong. And that makes the math collapse fast and model collapse. So math is bad, feedback loop is bad, and my talk is also bad and over. How do you use this work? All right, your students, here's how to do the work. We started in 2020, we built that, we found 78 risks. We adjusted it for LLMs like this with the black box thingy, and we thought about the LLM situation and we adjusted it to 81 risks, and there they are. But what I want you to do is take the risks that we wrote down and explained, and anytime you ever use an LLM for an application, think about those risks. How does that apply to my thing that I just built? Like, does recursive pollution really matter? In this case, maybe the answer is no, or maybe it's yes. But you should know the answer. You don't get to just like build it and hope that it's secure or whatever. So we are in a security engineering time of the dark arts. We're not sure where we're going. This is not the first time. We've done this before. We did this with software. We did this with mobile technology. Now we're doing it with machine learning. Same old, same old. You know, we have a chance to get in front of it. Oh, wait, no, we don't. We had that. That went by. Now we have to clean up our mess. Right, so use these data to make your stuff better and think about those things. And then you can go get some stuff in these places. That is my talk. Thank you for listening.
So we understand that it's after 5. If you got to go, you got to go. We're going to take a little time for questions. If anybody has questions for Gary.
And if you do go, please bring me a cocktail. It's after 5. Everybody's over 21.
Yeah, right. Any questions for Gary? Oh,
Yes.
we got one.
Stick around. I'll be here for a minute if you want.
What do you think the value of explainability engines is for mitigating risk?
Explainability is a tricky subject. And last paper I read was so bad, they decided to say that we should dumb down the way this works so humans will understand it.
I saw that.
Which is not what that means. That's not what explainability means. That's called bullshitting. And so I'm very concerned that explainability literature is not headed in the right direction. And there's a lot of optimism. You know, people would like to pretend that it's working. So there's money behind it now, but none of those things.
Yeah. Okay. Yeah. I know Microsoft has a big one that they keep on touting, but it's expensive.
Yeah.
And I'm not
You know, the good news about Microsoft is they build really great software. It works all the time.
Oh, yeah. Until Tuesday.
Yep. Anybody else? Don't be shy. Yes.
You bring up a good point with the like the cat.
Yeah.
But
It has great
I guess I'm
value to it.
I'm saying the question with a lot of assumptions.
Yeah.
I don't really know how it works.
Yeah.
You got a good.
You could say that statistically, if the thing manifests in the real world
Yeah.
with the mathematical rules, 83% cat in the physical world would look like that.
You're right. It just
So-
it makes a good joke.
Right. But I guess what I'm trying to say is, from a security standpoint, would you say how this like free software guys are touting? Oh, it will eventually sort itself out. Once that work,
No.
they work.
Let me
And-
tell you my biggest concern about the open source thing. So the open source guys are saying, we're gonna publish our algorithm, but they're not gonna publish their data set. That is not open source. Remember, this is a what machine. I'm not interested in the little tiny what machine thing details. That's easy to understand. You can, like I said, theoretically, we understand how all these parts work. It's just when we take the pile of what and we stick it in there and we instantiate that we need to know what the what pile is. And nobody's publishing that. Actually, only the Allen Institute is publishing that. So we like what they're doing, but the rest of the people are just making stuff up. And they're sort of hiding under the mantle of open source, which is, you know, I never thought it was more secure anyway. I mean, I'm a commercial software guy who got paid for a living to do security analysis. And I can assure you that nobody ever did what we did for Visa on their systems for open source stuff, because they couldn't afford us. And we're not doing it for fun. We're doing it for money. So, you know, take it as you will. And the many eyeballs thing, absolute baloney. It depends on whose eyeballs, not how many there are. So, yeah, good question. Anybody else?
I think we got one more.
Yes, one more.
One more.
Of all the risks that you analyzed, are there any that you feel like are not really feasible to address or could be too difficult to actually?
Recursive pollution is very not feasible to address. In some sense, that says we got to scrap the what machines we built so far out of the data that we didn't trust because we have no reason to trust it. And my own intuition, I have no proof of this, is that we cannot align a system we built out of a broken what pile. There's no amount of alignment and ex post facto training, even changing weights and trying to get rid of certain concepts, whatever those are in there, is going to work. Here's the weird thing. So as a computer scientist, it has always bothered me that we built a universal machine and it does some stuff and we bind it to a particular machine with a program to do something for us. but we built a universal machine, and then we get mad when it does stuff we didn't want it to do. And the question we should ask ourselves is, why did we build a universal machine for that? It's a Coke machine. It only needs 8 states. Build a DFA. Why did you use a Turing machine for that, you idiot? And I've been asking the theory people to please tell us security properties in the Chomsky hierarchy for 25 years, and we haven't made any progress in that. Instead, we're always building the big thing and getting mad when it does something we don't want it to do. The principle of least privilege, it's like it doesn't even exist. We're doing the same thing in machine learning now. Build the big thing that's sort of broken, that we can constrain its use. Seems kind of silly. So my view is we need to change our philosophy. In the 1940s, almost 80 years ago, it seemed like a good idea to build a universal computer, and it was cheaper, and we invented software to build particular computers. But now maybe we can build particular computers for particular things that can't do stuff that we don't want it to do. And we're not doing that yet. Shrink wrapping down to nothing.
FPGAs.
Yeah, well, FPGAs for us. 4 states, 2 states. All we need is binary. Okay, guys. Thanks for coming.
I'm sorry, there's one more question online.
Yeah.
Sorry, I didn't see this one. We gotta answer this one. Can you go ahead and ask your question?
Oh, voice of God, where is it?
Text if sound doesn't come through.
Yeah, go ahead and ask it.
He was asking about the best way to address prompt manipulation injection. He's also running into issues around feasibility.
Yeah, I mean, you can't address it ex post facto. So, will some clever person come along and always be able to make the thing misbehave? Probably, because we have an undocumented, underspecified API that we're using to program, and that doesn't work. English is a very terrible programming language. Terrible, terrible. It's ambiguous. Ever had issues texting people and they didn't understand what you meant, and then it led to big disasters? Well, imagine we built a program to do that on purpose. I have some cool stickers. Come get one.
All right, let's thank Gary one more time. Thank you.
Thank you.
See you all for the next cybersecurity seminar. Please take cookies.
Then what did you do?